Awesome. So I first thought of doing that in French, and then I realized that most of the words I had no idea how to say them in French anyway. So I'll do that in English. So for those that don't know me, my name is Baptiste Wicht, as I was like very well introduced. I've been working as a C++ engineer for 6 years after my PhD, and in total I've been working in C++ for more than 15 years now. So that's kind of almost a passion at this point. So it's kind of funny to talk about C++ in a modern presentation because C++ is actually quite old. Started in 1985. So it's far from a modern language, but it's been evolving a lot, especially in the last decade. So it started in 1985, and from there to almost 2003, almost nothing happened. It's kind of the same language, didn't change much. But then something changed in C++ in 2011 with the so-called C++11, and from C++11, every 3 years we got a new version of language, and not only small changes, but actually huge changes, making it almost a new language. For somebody that only knows C++03 and now tries to use C++23 or even 26, it's a totally different language. So we'll start with a brief history of C++. So I recently read a very good book, so I added some titles entirely unrelated to C++, but related to the book. So we'll see if somebody can pick that up. So in C++11, it's really the first step towards the modern C++. So we got lambda expressions, which is something we have in almost all languages now, but C++ didn't have. We got move semantics. So instead of copying things, you can move them from one place to another, which is very important for performance. We got the beginning of compile time expressions. Before, if you know C++, you can actually do everything at compile time with templates. That's extremely cumbersome, but it's still a very complete language if you do it with templates. With C++11, we started having some basic called constexpr expression. So you could do a function that is then not executed at runtime, but executed by the compiler at compile time. And we'll see later that this will come up more and more. We also got variadic templates, which are like very practical for like tuples and even pairs. And then a lot of new libraries. So until C++11, we didn't even have a thread library. So we could use POSIX thread, that's what almost everybody was doing, or use Boost thread. And a lot of these libraries actually came from Boost. So we got like a chrono library for time, an actual array, an hash map, some smart pointers, which also makes, we'll come back to that later because it makes a lot of, it's a very important in the current time. Then we got something a bit more small, which was C++14. I talked about compile time programming before. That one made a huge difference there. But if you didn't use it, it didn't make that big of a difference. We could get functions entirely compiled with much less limitations. We could do much more at compile time. Also got variable templates, even one more introduction of templates. A lot of improvements on the libraries introduced by C++11. So every time it is like more minor, but still introduce some important things. C++17 was a bit more feature-rich, I would say. So we got if context, which is an if that is at compile time. So you got the guarantee that the inside will basically only the if or the else will be at runtime. Everything else will be guaranteed to be removed. It still has to compile, so you cannot write stupid things inside. It still has to be C++, it's still validated, but it doesn't have to entirely evaluate, which makes a difference in templates, for instance. We also got structured bindings, which lets you extract elements from a pair or a tuple into variables. And if you iterate over, for instance, a map, you can get key and entry at the same time without having to access the pair values. And something a bit small but still very interesting is the guaranteed copy deletion. So the compiler now, before it was doing it, but you didn't have a guarantee that your copy was elided by the compiler. Now it's the case. And again, a bunch of new libraries, optional, variant, any, string view. And we got the first parallel algorithms. So before you could do stud find, for instance, or stud for each. Now you can do the stud for each parallel. So you can do them automatically in parallel on the STL library. And then another massive update. So they even picked up the pace with C++20. We got concepts, which are basically a way to put a contract at compile time. So if you've done template metaprogramming, which I expect probably not a lot of you have done, or maybe a lot of you ate, but you can now tell the compiler what you expect, because by default, a template in C++ just tells you you can put anything you want. And then if it doesn't work, I'll just drop a huge error in your command line, and I'll tell you mostly what's wrong. With concept, you can tell, OK, that actually needs to have a pushback function, for instance, or that needs to have overloaded the subscript operator. We also got ranges, which makes iterating over collections and modifying collection much easier. Before, we always add this pair of an iterator to the beginning and to the end. Now you actually got a range, and you can pass it around and modify it. We also got modules, which in theory should entirely change the way we write C++, using modules instead of simply header files and source files. It's a great feature, it's in the language, but there's not that much tooling support at this point, and applying it on a legacy code is so much work that nobody does it. We also got coroutines, which is a special way of doing parallel and async programming. We got the spaceship operator, which is a minor thing, but I only mentioned it because it has a cool name, which is less than, I should actually have wrote it here, less than, equals, and greater than, which makes a small spaceship, which really makes it much easier to write comparison operators for your types. And again, a few more libraries. I think the most important is stud format, which makes it like much more modern to do formatting strings, like for instance in Python. Bit smaller for C++23, we got the if conceval, which lets you do, again, is at compile time, but only if the value is known at compile time. That's another layer. An interesting one is a multidimensional subscript. So the subscript is the square brackets. Now you can have multiple values inside. For instance, if you get like a matrix type, it's more convenient for syntax. Stud expected also makes it nicer. We got stud print, which can almost replace all the stud cout and stud cr code we got used to. And finally, we got to the latest one, C++26, which is still not here, but it will be very big. So I call it a life-changing, but for most people it won't be life-changing, maybe only for me. So what we are going to have is contracts. I'll come back to that, but it's been adopted already in the standard, so we know we're going to have this. So a contract is something you put on a function. It's your precondition, postconditions, and could also be invariants. But currently that won't be implemented at this point. But we'll come back to that because it's important. We are also going very likely to have introspection and code generation, which is something that was missing. So you could now, at compile time, generate code. Or, like, for instance, get information about a class, like how many fields does this class have. It's very interesting because it's only a compile time, so there's no runtime overhead, which is generally something that C++ does very well. But a very common example is like you usually have a field with a class with 10 fields, and you want to dump that to JSON, for instance. In many dynamic languages, it's very easy. You just ask it for the list of the fields and its types, and then you generate JSON. Cannot do that in C++ because you don't have the information at runtime, but now that's something we can do at compile time without any overhead. Also, many library, even more context per improvements. We may get pattern matching, which is a very advanced feature, but currently it looks like it's going to skip to C++29. But a few points, maybe some you've heard. In December 2023, the NSA advertised to only get memory-safe languages in a new program, and the same for CISA at the same time. And there is a list from NIST and other lists as well of what is safe languages. And unfortunately, C++ is not in the list. And again, in February 2024, the White House said that any new projects related to the US government should only be written in a memory-safe language. So as you can imagine, this stirred a lot of controversy in the C++ world, and also in others. We are not the only one that are in that case. So is C++ doomed? You cannot write any new code in C++. So I don't think it's doomed. But I also think there's a lot of legacy. So C++ is much safer than it used to be. We got smart pointers now, which means you don't have to do new and delete. You don't have to do malloc and free, things like that. Everything is done directly by the compiler. We get containers with bounds check. We will get contracts in C++26, so you can tell your function that parameter only can be from like 0 to 10, or that one, the output can only be in a range of 10 to 11, something like that. That will definitely increase the safety. We also get in C++26 the hardened standard library, which is an option to make the standard library much more secure. One example is that normally by default, not all the functions in a vector, for instance, are checked for bounds. So for performance reasons, some of the functions are not checked. So if you access the element 1000 in a vector of size 20, you will access something in memory, you just have no idea why, and the vector will not complain. But the main issue currently is that C++ is not safe by default. Everything I mentioned makes it safer, but you don't have to use it. You can still use only raw pointers, new and delete, or even malloc and free if you want, and write code that is absolutely unsafe. And as I mentioned, for a vector, for instance, if you use the subscript, you don't get a bounds check. But if you use the @ function, you get a bounds check. So depending on the way you write code, you will get more or less safe language. And this is very contrary to something like Rust, where safety is by default. So in C++, you have kind of speed by default, the unsafe version of Rust, and then you can enable the safe version by coding it according to guidelines. So a lot of the safety is actually behind good practices. So you can write very safe, very good C++ code, but you can also write very bad, very unsafe code. And validating guidelines is actually very difficult. One thing that has also been happening, so if you are a C++ developer, you likely know what is undefined behavior. So it's something in the standard that is known to be undefined. And usually, if you want a safe behavior, you don't want it to be undefined, you want it to be defined. Even if it's an error, you want it to be defined on something. And this has been improved recently. For instance, in C++26, we got one case being removed from the language. So if you use a variable that is not been initialized, it's not undefined behavior anymore. It has to be set to a fixed value by the compiler. It can be any magic value that the compiler can use, but it's guaranteed. And the good news with that is you can already recompile your existing code with just one flag, even before C++26. Just tell the compiler to do that, and you will already have that for free. Another good thing is that in C++, everything that is const_expr is already undefined behavior free. So if you write only code that is const_expr, since it's guaranteed to be able to run at compile time, it's also guaranteed to be running without any undefined behavior. We can also remove some things in the standard library, so something that are not undefined anymore once we use the hardened version. And currently, the committee has been planning to remove most of it, ideally everything. That's something that the committee has already talked. And there are many more papers for the next few versions, at least C++29. We'll probably see a few more. Hopefully, all of them will be removed. One more very interesting thing. So I mentioned before, C++ is kind of unsafe by default. It's a bit pessimistic, but that's kind of the case. So what if C++ safety was not a choice, but the default? And just very recently, that's probably been triggered by the controversy. Herb Sutter, one of the members of the committee, proposed a new paper, which is to provide core safety profiles for C++26. The idea is that everything I said before was unsafe. You could not write it, and that will be detected not by a guideline, but only by the compiler. And there are 4 big parts. Not everything can be addressed by a profile at compile time, but bounds checking on containers, on pointers arithmetic will be addressed. Types, every typecast that will be unsafe, for instance, will be simply compiler error. Anything you do manually with memory will be an error. If you dereference a null pointer, will be an error at compile time. And same if you do like lossy conversions of arithmetic or overflows will also be detected. So the idea will be that you can enable the option and switch to a safe profile instead of switching to the default profile. But maybe something we get for in the future, but that will very unlikely be in C++26, or at least will not have the compiler support. So maybe a few words on Rust versus C++. I'm not a Rust expert. I've only been doing Rust for a few months. But I believe that both languages have value. As I said before, Rust is safe by default. You can do unsafe things in Rust, but you have to say unsafe. So there's already a big red flag in your code that you have a block, it's unsafe. And usually, you try to avoid that. On the other hand, C++ is unsafe by default, but you can write safe code. So it's kind of up to you. One thing is that C++ is very concerned, probably too much, about compatibility. And on the other hand, Rust is much more liberal. So since it's been created, they have broken some code a lot of time. So if you wrote code 8 years ago at the beginning of Rust, it will likely not work anymore. So that could be a concern. On the other hand, C++ has always guaranteed API compatibility over time. And this is actually probably a reason why it's unsafe, because there are many things they cannot remove because they want to be compatible. Libraries for C++, from what I've gathered from my small projects, probably I'm way out, are well above Rust. But it's really picking up. I'm surprised in the last probably 1 year, the libraries for Rust are really getting more and more. I was extremely disappointed by metaprogramming in Rust, but that's probably because I have a big bias towards templates. I really like templates, and the first project I did in Rust was porting templates to Rust, and that's a very different beast. You can do metaprogramming, you can do everything at compile time with C++, Rust is not the case. On the other hand, when you do templates in Rust, they actually compile in no time. When you do them in C++, you have time for coffee between your compilations. So I still believe that both languages are very likely to live long and prosper. Sorry. So I think there's value. C++ have been here for longer than I did, and it's probably going here at least as long as I do. And hopefully Rust as well, because there's a lot of value. So what can we do today for C++? So I mentioned a lot of features that are in the future. One thing we can do is upgrading compilers to get the latest warnings, to get the latest checks. Use some recent compiler options. For instance, the one I mentioned before is the trivial auto-var init pattern. We can initialize all variables that are not initialized. Use the hardened standard library if you can. And then it's all down to guidelines. So always use smart pointers as much as you can. Use the sanitizers, which is something that started quite a few years back actually, you can get checkers into your code that will run at runtime, but that will actually prevent a lot of the unsafe stuff. But usually they are too slow for you to run them in production. So you do run them into unit test, into continuous integration, but then you kind of give them up, which is not ideal. Everything you can do in a compiler is great. And obviously if you can follow C++ core guidelines, but there are a lot of them. So word to the end, I think C++ will entirely survive the current situation. Even though the world is shifting toward memory safe language, I think this will do very good things for C++. It will become safer. It has basically no choice. C++ 29, I expect that we will see many, many things into the standard only there for safety. And that's it. Any question?
So thanks a lot, Baptiste, for your presentation. So it's been terrific about reading all these new features that are coming. Now the question to the audience. Do you have multiple questions? Yes?
I wanted to ask, how do you see memory safety versus logical errors? Memory safety are not the only problem, obviously.
What do you mean by logical errors?
Like if you make some implementation faults, or you're, like you have to test them.
So that's a good point. So memory safety is only one part of it, and that's kind of, I would say, the easy part, because that can be checked often at runtime. A bounce check is very easy to implement. If you are below or higher your range, you're just out. Logical errors, compiler can do some things, but not much. In the end, there's still a lot of value in the developer itself. Maybe one day with AI and compilers will be integrated and there will not be any bugs. But I think that people are focusing on memory safe languages because memory issues, if you look at CVEs in general, there are more than 70% of CVEs that are caused by simply out of bounds, things like that. So first, everybody wants to address like the big ones, and then I guess that everything else, we can probably get better compilers. I'm not sure we can do much into the language to avoid this, but maybe I'm wrong.
Thank you for your talk. That was very interesting. I have just a small question about a library that you mentioned in C++ version. I think it was, no, it was even before. Yes, std optional.
Yep.
Coming from a Rust background, is that something that is similar to the option enum type in Rust or not?
Kind of, yes.
Kind of.
Yeah. So you can either get your result or nothing. Okay. But it's not. I think it ties more with. Did I write it down? I wrote stud expected. Yeah. Stud expected is probably more the case because you expect something, but you can get either what you want or an error. An optional, if there is nothing, it's still not an error. Mm-hmm. It just does nothing. You can have. It's the same as having a Boolean plus something. Both are valid. With the expected, then you could have more something close to Rust, and you would have you will not have like the syntax stuff with like unwrapping and like propagating, but you could still get what you want or an error, and then what you want without throwing an exception.
Could you, for example, use something like the if-let statement that you have in Rust with that type? With that option type, or is it something that we can't imagine in C++?
It may come. You can't yet, so you can still propagate it yourself, but it's not as clean, no. But I think it may come at some point, but they will have to add the language side of things for it.
Thank you very much.
You're welcome.
So we've got another winner here. Who's got the token?
Yeah, thanks for the talk. I'm very, very curious. What was it with C++ templates that you had that was painful to port to macros?
Sure.
Please explain.
So I started with probably the worst kind of project. I ported the next expression templates library, which lets you do like linear algebra, so you can write huge expressions with like matrix A multiplied by B plus something multiplied, things like that. That works, no problem. There are some issues. For instance, you don't know the types of a generic when you are inside the code. So if you want to do code that is slightly different for a float or for an int, there's no way to do that. That's one example. And that code is also vectorized, but for instance, the portable vectorized library in Rust does not allow me to do that because some of the code is actually a different library for float and int again. And then if you want to do some smart things, like I want to multiply two matrices, that's fine. But if the first is actually a scalar and not a matrix, I want to do it differently. But again, you're stuck. You can do with wrappers and stuff, but then the syntax is less obvious. But that's kind of a place where C++ actually shines. So that was maybe not a fair example. Yeah.
Thanks a lot. So is there one last question?
I have just one question also for Baptiste. What is the cost on the code size with this new improvement that you presented on C++? Is there any price to pay on the code size? Or because we used to have C++ also in embedded systems, is there a drawback to use this new feature on embedded systems? We know that, for example, the exceptions were never used in embedded systems, and streams was also not very popular in embedded systems. Are there in these new safety stuff things that we should not use in embedded systems?
I don't think so. So I don't think it's becoming worse. A lot of it will be like reduced at compile time. So you got your contracts; they will just be checked, and mostly at compile time. So it's not entirely wrong. Some of it will be added at runtime. I don't think we have nothing like really significantly increase the size. Of course, if we add like bounce checking code, the code still has to be there at runtime as well. Otherwise, it's kind of pointless if you cannot elide it entirely. But I don't see a huge impact on that side. But it's also probably not going to make it much better either. It still compiles to a very large binary.
Good. Thanks a lot. So I think you deserve a round of applause.
Thank you.